Swayam Prabha. Digital India. Educated India.
So, you guys are from, most of you are from Tamil Nadu, right? All are Tamil Nadu. Nice. That is the indication. Okay. So, what do you want to do in your life? Class முடிஞ்சிட்ட அப்புறம் ஹாஸ்டலுக்கு போகணும் சார் சொல்லாதீங்க. See, I am a Telugu person. I learned Tamil. I am trying to speak. If there are some grammatical mistakes or even meaning mistakes, you accommodate. Try to adjust and try to understand what I am speaking. Okay? So, what do you want to become in your life? Did you question yourself? Why? That is targetless, aimless. Why no? No one is speaking? Emma, enna peru? Dhanalakshmi. Lot of money. Okay. Lakshmi itself is money. Dhanalakshmi means double money. Okay, ma? Okay. Jokes apart, what do you want to become? You want to say something? What do you want to become? Study well and get a job. Well, that is a good job. But any of you want to do research in this life? Or it is postponed for next life? Next life, huh? This life, okay. So for that, what do you need to do? What do you want to do? Higher studies you have to do. For that, what you need to do? To get into IIT. Have you ever thought of IIT? Have you first time? How many of you have heard IIT as first time? You are IITs. IISers? All of you heard before coming over here? Oh, you are much advanced. I heard about IIT when I got a job in IIT, by the way. I'm just joking. But before going to IISc for my PhD, I heard about IITs. Okay, let me tell you about myself. I am Rajakumar Balla. I hailed from Andhra Pradesh, a remote village, seriously remote village. The village is like, I have seen electric bulb when I was 12 years old. I was born in 71. Don't calculate my age is 53 and entering 54, okay. I mean completing 54 soon, okay. So I have come from that remote village. Forget about roads, transportation and all. There was drought for 7 years. We were eating one time in a day. Seriously. There are many people who died of hunger. Such a very, very low profile, right? Now what am I? I am a professor at IIT. I am very proud to say. How did I become? Nobody gave me job. I earned this degree. How? Hard work. Work hard, not hardly working. Work hard. So what is that I have done? Let us see. Okay. Before that, I have done my MSc in Andhra University, Visakhapatnam, whose first Vice Chancellor was Sarvepalli Radhakrishnan, who was the President of India. Right? So these are inspirations, that's why I am saying. Then I went to IISc for Bangalore for PhD. I don't even know, you know how I got to know about IISc? When I was reading Quantum Chemistry by A.K. Chandra. My classmate Sridhar Rao was there, Sridhar. Hey, my brother is doing PhD with A.K. Chandra, he said. I used to ask a lot of questions in the class on quantum chemistry. Then I asked him, give me his address. He gave me, I wrote a letter and he replied saying that those days letters. Yeah, it is, you can do. Then I wrote GATE. Then I wrote CSIR. Okay. Then I wrote IISc entrance examination. I don't want to tell the results, so you know what it is. So I did PhD there. Then I went to the USA for a postdoc, where I worked in, there is a place called, you know NASA, right? A part of it. Okay. It's called National Oceanic and Atmospheric Administration, NOAA. It's affiliated to University of Colorado, Boulder, Colorado. Okay. I was there for about 3.5 years or 4 years. Then I came back as an assistant professor. So why I said this story is, sky is the limit to all of you. Yeah. You might have come from very remote village. Don't think that I am from very small village, sir. I don't know anything. Nobody is guiding. No, nothing. You are the guide of yourself. You are the torch bearer for yourself. Okay. Okay. Then while doing research, I thought, do I do some nanochemistry? Do I do some chemistry which is regular synthesis and all? I thought about it. No, I should do something different which is useful to the society. So what did I do? I have done atmospheric chemistry, where I can use physical chemistry methods to understand the atmospheric chemistry. See the beauty of it. What is atmospheric chemistry? What is global warming? What is ozone? How much ozone is left? How much ozone is being created? What nonsense is going on in the atmosphere? Why the ozone hole is formed? So many questions triggered. Those questions were drilling my head. Not able to sleep. We need answers for the questions. Right? Asking questions is one thing. Mad fellow, keep on asking. You should get the answers. So want to work. So how do we understand the chemistry in the atmosphere? I see you, right? What's your name? Abhinaya. Where are you from? Ooty. Oh, so chill. Okay. Small carrots are there, no? They're very tasty. I know. Okay. I went some time back. Okay. Abhinaya, how do I see you, right? Do you see me? Suppose you cannot see me, what is the reason? Not blind. That is different. If you are not able to see me, what must be the reason? There must be something in between us. Some wall or turbidity or some, you are able to see. But you are able to inhale oxygen along with nitrogen, right? Me too. Of course you are inhaling nitrogen too. You cannot separate nitrogen. You have a filter here? You don't, right? So you inhale oxygen, nitrogen, and use oxygen and send out nitrogen and carbon dioxide too. So, but how do you know this is only oxygen you are inhaling? Something else. Lot of pollution, right? Many chemicals we are releasing into the atmosphere. So, if we are releasing lot of chemicals, they do some damage, right? You know what damage? We can't see them. If you see a thief, no? Hey, that fellow is a thief. Beat him. No? We catch him, right? Hey, not you, man. Okay. Hey, this is the thief. Catch me. Okay. The thing is, it's invisible. You can't see the molecules with the naked eye, can you? Unless you have the spectrometers in the eyes. Right? That's only possible in Hollywood movies. Right? So, what do? We need to understand the chemistry, right? We need to measure the chemical reactions. We need to see what the hell is happening in the atmosphere. Actually, what is happening is hell. You can't see. You can't see anything, you know something is happening and you need to figure out what it is. You understand? My English is okay with you? Yes, sir. Very good. That means I am speaking understandable English. Good. So what the hell is happening is actually hell is happening. How do you recognize them? You need to have sophisticated instrumentation. You need to have spectroscopic techniques. Beautifully you can design the spectrometers. You can build the spectrometers for your convenience, for your requirement. See, my shirt size is 45. In the market 44 is available, 46 is available. It is custom tailored, right? If I wear 46, it will look dabba. If I wear 44, it will become blouse. Neither of them not are good. So I need to wear a shirt. So you need to tailor make the equipment. That is what we have done. I am very proud to say the best lab in this country and one of the top 10 labs in the world we have built here. Okay? We have built a spectrometers here to understand the atmospheric chemistry, which I will present to you now. Any of you can see, send an email to me, you can see my website, you can take a picture without me, no problem. Huh? You took, huh? Huh? You have a camera in your eyes? Okay. Okay, fine. Not me. Huh? I look very ugly, I know that. Huh. Okay. Now, you can write to me, I will reply, or you can walk down when you are here. And I request all of you to visit the lab and in batches and see the lab. You won't see this kind of lab in the country anywhere, for sure. If you think that I am boasting about myself, not at all. Even if I look at that lab as an outsider, I will be mesmerized. That kind of lab we have built. I will show you what it is, okay? Before that, I will give kind of some introduction. You need a break till 4 o'clock if I speak like this? I am sure you don't, but I need. Okay. There is one side of it. Another side what I do is, I do combustion chemistry. You use biofuels, right? Why? What is the difference between the fuel and biofuel? Okay, good. Nature. If you combust both of them, what do you see the difference? Abhinaya. Dhanlakshmi. Hey, what's your name? Mr. Narendran. What do you see? I give you biofuel. I give you fossil fuel. Right? I will ask you to find out when you burn, what difference you find. I will give you all equipment to you. Fossil fuels will give more toxic. Oh. Suppose if I generate gasoline from biofuel, bio waste and fossil fuel also. Both are gasoline. How does it matter? When you combust both of them, give same thing. How do you know this is, unless you put a black shade to the biofuel and what is that yellow shade to this kind of shade to the fossil fuel, right? We can't, can we? So, they more or less they give similar compounds, but the advantage with biofuels is the carbon dioxide which you are releasing, it is taken from the nature, biosphere, and you are giving back to it. It is a cycle. The same carbon dioxide will be utilized by the plants for their growth. But fossil fuels here are taking from the Earth's crust, deep inside the earth, and you are taking it, and you are burning it, and you are releasing carbon dioxide into the atmosphere. What great job you are doing? You are screwing up the atmosphere. See that? So you are actually warming up the globe by increasing the carbon dioxide content. And all the chemicals, whatever you get the same. There is no doubt. But it is the cyclable things. Okay? So biofuels also we thermally decompose and see what kind of chemistry is happening there. As it is, you have to cut this part, okay? No. You record, but you remember this. See, some propellants which are used for ISRO and DRDO, we thermally decompose in the lab and see the chemistry because it's used for the rockets in the warfields. You have to cut this. It should not be telecasted, okay? Yeah. Fine. Now, you see this? It is one side it is atmospheric process, another one is combustion process. And both the pillars are supported by experimental and computational studies. Both the pillars are supported by experimental and computational methods. That means I do both. Let us see what we do. Before that, I will give some introduction to about the atmospheric chemistry. Now we will talk about atmospheric chemistry. Where is that? All of you went to Marina Beach? I know. Okay. You have seen Annadurai and all those things? Took pictures? But that is where our life starts, right? Biosphere starts there and goes up to 10 kilometers. Or what is that? Where is that? Yeah. Okay. Fine. Now the thing is, if you look at this is the troposphere. You see this is 0 degrees and the temperature is on this side and pressure is on this side. Altitude is this. You see that? When you go up, who is from Ooty, Abhinay? When you go up to Ooty, you will feel very chill. The temperature goes down. Hey, ask her to take all of you there. Okay, she should host. Okay, now, but this is negative. But after some time, it is paused. There is no change in the temperature. Let's call it tropopause. Because of many reasons, we will not get into that, okay. And then you see again increase in temperature. Although it is negative, there is an increase in temperature. Why is that increase in the temperature in the stratosphere? Why? Any guess? What's your name? Niveda. Iveta Sri. What is the meaning? Different, that's why I am asking. I know, Veda. Oh, okay, good, very good, yeah. Why is the temperature rising in the stratosphere? Iveta Sri? What's your name? Mahalakshmi. Bhagyalakshmi, Mahalakshmi. Dhanalakshmi, Bhagyalakshmi, Mahalakshmi, many Lakshmis are there. What is the reason? What's your name? Varsha, rain. Yeah, tell me what is that? Why the temperature is increasing there? No idea? Think about it. It's easy to say, right? Yeah. Last by. Always smiling, yeah. What's your name? Why shorts? Mohanlal he cannot have that name. He doesn't have a patent right. Yeah. Fine. Okay. People call you Lal, huh? I know. The way he is called. Why the temperature is increasing in the stratosphere? What's your name? Uma, yeah. Uma is also name of Lakshmi. My goddess, I know, yeah. What's that? Nitrogen. What nitrogen does? What do you do? Accumulation of carbon dioxide in stratosphere. You must be going and exhaling there. Like this, huh? Then? Actually, a lot of chemistry happens. Exothermic chemistry happens over there. That happens here also. In Ooty also it happens. Chemistry is more heterogeneous over there, not homogeneous. Chemistry happens on the clouds. Lot of exothermicity, lot of heat is generated. Okay, fine, but still it is negative temperature, it's cool. It's not that some 200 degrees Celsius, no, you can see the scale. But while it goes, the temperature is zigzag, you can see the pressure difference here. 100 millibars at 10 kilometers, how many millibars is 1 bar? How many grams per 1 kg? So how many millibar per 1 bar? Very simple, man. Bar, millibar, don't think the other bar, okay. See, all of them are laughing. Okay, next, we'll laugh in the evening, man. Next one is, you go to 20 kilometers, one more zero is gone. You see that? This is 100 millibar, this is 10 millibar, this is 1 millibar, this is 0.1 millibar. For every 10 kilometers altitude rise. What does it mean? It is uniform. If you draw the altitude versus the pressure, okay, altitude versus pressure, it is dropping, right? It is dropping down with the increase in altitude. Pressure is dropping down, linear. But it is not the case in temperature. Temperature is going like this. It is dancing. Okay. So, why do we need to talk about this? We should know about our atmosphere before doing the chemistry. We need to mimic these conditions in the laboratory before planning for any chemistry, any experimentation to be done. Okay. Now, let us not worry about the mesosphere, thermosphere. He will go to, Lal will go to ionosphere and he will become ionized. Okay. Now, look at this. What are these? Oxygen, nitrogen, and there are trace gases here. We'll talk about them. And carbon dioxide here, and argon is another plenty one. The most useful one is this one, and the next useful is in this one. That's what we think. But argon is highly useful, carbon dioxide is necessary for the biosphere. Everything is essential. But what is not essential is what you are producing. What have you produced? The trace gases. What are the trace gases? We'll talk about it. Okay, now you see, if you look at the concentration wise, methane is very high. See, nitrogen is high, carbon dioxide, oxygen is high, water is of course very high, carbon dioxide is high. Then argon falls here. You see that concentration of argon is next one. And methane is the product of biosphere. Okay, and then lot of concentration in ppm, and then it goes to ppb. This is all these crazy guys. Who are those? Chlorofluorocarbons. Did nature produce them? We have produced. Good guys. We know how to spoil it, right? Nice class, right? Some idiot will get angry. Why this class is going so smoothly? Leave a monkey inside. That's all, gone. All of us will dance along with monkey. Oh, like this we do. Right? Now, entropy will increase, right? Decrease or increase when monkey comes? Huh? Lal. See, it's very, very bright smile. What's your name? Lokesh. Chandrababu Naidu's son's name. Okay. The great leader, no? Okay, this to be scissored, okay. Now, chlorofluorocarbons we have produced a lot. Am I right? And they have damaged so much. We'll see how much they have damaged. What are those trace gases? Look at this, concentrations. 1 into 10 to the minus 1, 2, 3, 4, minus say 8 or 9%. Those guys are so small, it is not that how big you are, how dangerous you are is important. Right? You can be very small, but you can be detrimental to the entire classroom. Keep on making noise and no concentration. Right? These are the guys who has spoiled the chemical equilibrium. The ecosystem is disturbed. Seriously, it is disturbed. Okay, you see the Chapman mechanism. Go and see in the internet what is Chapman mechanism, and then you see how the ozone is lost. Okay, I will not discuss those things. Greenhouse gases seems to be very low in the concentration, but why do they play a very important role in the global warming? Is something which need to be understood. Before that we talk about it, we need to understand what is global warming. I'll tell you when it comes. Okay, and by the way, now argon is about 0.1%, almost 1%. It comes to 10 to the minus 8. If you look at this, these guys have controlled the entire globe. All rest of them are just watching the fun. Right? Oxygen is plenty, nitrogen is plenty. Could they do anything? He is coming and it's like coronavirus. How much was there? Very small. Killed a lot of people. See that? Now, what is the size of the coronavirus? Not my size, definitely. Where you have to see nanometer, microscope no, nanoscope you have to use to see that. See that? So these CFCs are like that, very dirty guys. We produce only dirt, no? That's what our job. Now you see, what is this pollution? Look at that. You use all this. This is Delhi. You see how many poles you can count? 1, 2, 3, 4, 5, 6, 7, probably 9. Look at that. You can't see anything. You can't go at more than 20 kilometers. You go and kiss the other car. That's all over. He will come down, you will come down, and will beat each other. That's what will happen. Now you see that. Very dangerous. And health, how much health get affected? All of them have respiratory issues. Unless you have artificial lungs, which are immune to everything. That's not possible. Okay? Now, Look at this. A day before lockdown, the India Gate. If that is the Rashtrapati Bhavan, if you stand like this and see, this is what it is. Okay, and if you during the lockdown, see that so clean. You can see the effect of your vehicular emissions. That's what I was trying to tell you. And before lockdown is this Himalayas, Chandigarh, from Chandigarh. And start of the lockdown, you can see. After 1 month of lockdown, you can see the Himalayas. Maybe for 300-400 kilometers away, but you can see very clearly. You understand this? See, all this is created by you guys. That guy will, Lal will go, you give him a motorbike, he will go at 120. He doesn't know how much pollution is creating. Right? Because he want to show the actions of Mohanlal. Right? Yeah. Fine. Now, let us go into the, okay, what chemistry we are talking about? Homogeneous chemistry. This is daytime. These guys, OH and HO2. How OH is produced in the atmosphere? Hydroxyl radicals, I'll tell you. That is, of course, water can be photo-dissociated and produce OH radicals, but simple thing is ozone with some light in UV light, less than 310 nanometers, what would happen is O2 plus O in singlet D. You know what it is? I am sure what you know this. Huh? What is that? Singlet D? Were you not taught term symbols? You are first year students or second year students? No, but this should be taught in first year. Some colleges taught, some colleges did not. Okay, anyway, it doesn't matter. It is a singlet state. Okay, you know what is singlet? 2s plus 1 is 1. That is S is 0. When it will be? 2 electrons are like this. You should understand immediately. D state is D state, you don't worry about all that. So when you use this, O plus, that is singlet D, and H2O, 2OH. This is a straight production of hydroxyl radicals. This is a straight production of hydroxyl radicals, plenty. And the entire chemistry in the atmosphere is surrounding by that. You see, it is produced, and what it is doing is important. See, hydroxyl radical react with RH and it produces, see how many chemicals are being formed here? RO, you know all these symbols, RO2, ROOH, this is acid, and nitrates and alcohols, many things are formed. So the point here is, you think that you are releasing just methane, but what you are producing is all kind of crap in the atmosphere. You have acid, you have ester, you have everything, you have cake, you have chicken, everything there. Because you started, you take acetylene, from acetylene you can produce entire organic chemistry, right? Yeah. You need some reagents. So in the atmosphere, photochemistry is very important. And the chemistry with OH is important. Okay, that's what is happening in daytime. Night time, look at him, I'll eat you, that is summer sun. Okay. Next one is night. Moon is cool, but nitrates are they play nighttime chemistry. I mean, all nitric acid rains and everything forms because of this chemistry. So nitrogen is also important. But if you add upon, then acid rains become predominant. Have you ever heard of fish falling from the sky during the rain? You haven't heard? You heard, right? There are people who caught the fish and ate. No problem. Fish is fish. See, that means something is happening over your head. So you are creating such an atmosphere over there. What's your name? Abhinandan. You remember this name? Very prominent name. What was it? Yes. Good. You should know at least the significance of your name. Okay. So the nighttime chemistry plays very cool. Daytime chemistry is important here. Nighttime chemistry also. See, the thing is, you are releasing anything, it is creating chemicals in the atmosphere. That's a basic point. Okay. Now you see. And heterogeneous chemistry, you may think that, sir, is all gas. Where is the heterogeneous chemistry? See, when it is a cool atmosphere, clouds are formed. It is not just clouds, they are the pellets, ice pellets floating. You go and try to land over there, it will crash. Because it's an ice pellet, you cannot pierce through the cloud. It's a solid, it's not a gas cloud anywhere. Therefore, air crash will happen over there, but you don't go to that high. So, but when cold trap is there, all hot gases go and sleep there, obviously. See, how do you do the distillation? You boil it and cool it, right? You boil somewhere and cool somewhere. So, you release the gases here and you have the, where are the cold places? Northern hemisphere and southern hemisphere. But northern hemisphere, the geographical situation is like Scandinavian mountains. So, very non-uniform. The gas distribution is not uniform. Therefore, the loss of any chemistry that happens, the loss of ozone because of the chemistry on the heterogeneous phase is very less. But when it comes to southern hemisphere, if you take the globe and stand and see like Vishnumurti, what you see is a big hole here. That means all ozone is gone because of the chemistry that has happened, that chemistry happens so uniformly, no mountains there, it's all oceans. You understand? So, in the northern hemisphere, the loss of ozone is less. In the southern hemisphere, the loss of ozone is very large. Okay? That's very important. Okay? So, now people are talking about, you know, the aerosols. Have you heard of aerosols? What are aerosols? Huh? Yes, speak. So, what is the size of aerosol? You should know. Try. What's your name? Bhuvaneshwari. Okay. Tell me, what is an aerosol? Have you heard of what is your name? Madhumita. So, what is an aerosol? What's your name? Indumati. Typical Tamil name, right? Yeah. So, what is an aerosol? No idea. Get an idea, Sirji. Yeah. Lal? What is the? No? Lokesh? No? Anyone who knows about aerosol? It is the suspension of or dispersion of the particles in the chemicals in particle size. It starts with one molecule and it accumulates more and it conglomerates more and become bigger particles, and it can be a small chemical particle which is formed of several molecules, and then water accumulation on that, and water accumulation on that, water accumulation on that, it becomes cloud. That is called cloud nucleation. Cloud condensation, when the pressure is low and atmosphere cools down, then the cloud condenses and you get the water. And the aerosol also comes down. The climate, what you are seeing that in Delhi and all those pictures, what you are seeing is because of the dispersion of many aerosols. Light gets scattered, so you lose the visibility. You understand? This is what it is. And now, lot of chemistry is happening inside such aerosols, but I will not get into that, but you can see that what kind of chemistry, bulk diffusion and all kind of compounds are being produced here. So, you can in the laboratory, you can actually form such a bubble, heterogeneous bubble, aerosol internal surface, and then you internal place, and you can do some reactions, bubble chemistry, people are doing. Richard Zare from Stanford is very popular on that. So, this is very important because some reactions can happen. You don't know that reactions can be so critical reactions can happen in such a small place. You understand? Clear? Okay. Now, see, now let us go into our business. After good introduction, we will get into that. You see, what is x-axis? Distance. 1 meter up to 10,000 kilometers. And what is y-axis? That is the age. Suppose a molecule you release into the atmosphere, it lives for 10,000 years. It would go to a year span of, it can survive in the atmosphere about 100 years and more. That is the scale. Understand? Where CFCs fall in? See, look at that guy. They are there. Those guys can survive for 645 years free and 12, CCl2F2. 645 years it can survive and kill entire ozone around it. So, you don't have the vaccine. So, you have released tons and tons of CFCs and you are suffering with that. You understand? Okay. Now, this you understand? No. So, if I tell you what is that propane? That's propane. Propane, because I don't have the specs now. Okay, propane, it survives for, it goes up to 100 meters, but it survives for 1 hour. That means it gets reacted, it's eaten away by the hydroxyl radicals. See that? Okay? And now, let us not get into this other part of it. So, now you see this chlorofluorocarbons. Now we are talking about 645 years. How many we have released? This is freon. And you see that up to 1975 and up to 1990, the usage was so high. What people have done is, like Henry Ford Research Foundation have produced thousands of metric tons. So what they have done is they have dumped everything in containers and dumped in the sea. But that is sea is salt atmosphere. One day it will be corroded, everything will come out. Temporarily you may think that you have sealed, but it will come out. See that? What we have done is nonsense. Without that, AC doesn't work, fridge doesn't work. Amma, cool thanni irukama. Amma kudukka mudiyadu. So you have to use it. When I come here, nice air conditioned room should be there, right? So use it. That's why we try to find the alternatives. Now freons are not used. Still you may get in India, that's a different case. Understand? But they are banned. So my audio is okay now. So the best place is here. If you put here, if you turn this side, voice goes away. If you turn this side, so many people do that mistake. So this is the place. Below the second button. That will catch very good. Okay? Fine. Now, you can see number of kind of freons we have used. Let us not worry about it. We know that enough damage we have done. Very clear. Right? We don't care. You eat the banana and throw the shell in next house. Throw the skin in the next house, right? Sapte? Vadivel Madri. அங்க விவேக் இருக்காரு, அவர் என்ன பண்ணுவாங்க? No, he is much generous. What he will do, eat jackfruit. What is jackfruit? பலாபலம். சாப்பிட்டு அந்த ஸ்கின் இந்த வீட்ல போடுவாங்க. நீங்க ஒன்னு கொடுத்தாச்சு, நான் எவ்வளவு கொடுத்தாச்சு? Generous. So you do something to the system will give you back so adversely. Right? But if Vadivel throw 100 rupees, he will not give 1 lakh rupees. Definitely not. So do good, okay, happy. But do bad, I will give you back. This is the policy. You understand? So you try to damage something. Why tsunamis are coming? Because globe is warming up. Great lakes are gone. They become the rivers now. After many hundreds of years, they will become the deserts. Because you are screwing up the atmosphere. Clear? Okay. Now, all boys and girls are playing here because ozone is protecting. Ozone concentration is high at 25 kilometers. This is a standard website material. Let us not go into the details. Okay. Now let us come to the chemistry part. Okay. You have a chemical, you have a molecule, and when it is released into the atmosphere by any means, anthropogenic, natural, bio, whatnot, or you compost something will come out, that's all fine. When it comes out, it gets exposed to the sunlight, right? You see the light, correct? When it gets exposed to the sunlight, it gets photodissociated, right? If you eat 50 idli, what will happen? You will break down. You absorb so much light, you get disintegrated. Fine. And another thing is, these hydroxyl radicals are there, you see that? Suppose you release some ethane. You release ethane. CH3, CH3. OH is there. It abstract here, it become water. It abstract this one, it become water. It abstract this one, it become water. That means the molecule loses its identity. That is the chemistry initiated by the photochemistry, but it is the indirect one because OH is formed first. The direct one is the molecule itself gets photodissociated. So whether the chemistry happens or photochemistry happens, chemistry is happening. The molecule cannot survive. It will be killed. You throw some plastic dabba into the ocean, I mean sea, what will happen? It will come back. Because it doesn't keep, nature doesn't keep anything with it. It will give back. Correct? So be careful of what you are giving. Okay, that is photochemistry I have taught, and free radical chemistry I told you just now, and the heterogeneous and multiphase chemistry we will just reserve it for some time. So what are the oxidants here? Ozone can react with the molecules, NO3 can react, OH can react, O triplet B, singlet, doublet PCl, O singlet D, many things. So how fast this, see how, if the compound is released into the atmosphere. How do I know this molecule survive for this long? Simple. We know the molecule will survive for X time, sorry, T time, not T time, T time, okay, depending upon how it reacts with the molecules, existing radicals, right. Suppose it is reacting fast, gone. You go to the 10th floor, to come down to the floor, what you need to do? You need to take the lift or the staircase. Somebody want to come fast, if he jumps, he will go up super fast. So that will die. You understand, no? So the chemical compounds which are reacting faster will lose their identity very fast. They are disintegrated, they decomposed, they lost their identity faster. But slower, they will survive very long. Such molecules are your CFCs. They cannot react with anything. We are stable. You can't do anything to me. I am very stable, strong. Touch me, you can, if you can. CFCs are such molecules. Only photochemistry can kill them. But unfortunate thing is, again those radicals will join together and form again CFCs. They won't die. Devil never dies. Is it devil already died, no? Pei sathipoiduma. Already sattapram da adi pei aipoiduchi. Correct dane? How can it become again it will die? No. So these CFCs are like that. What's your name? Karthikeyan. Popular name. Who is that person? Murugan Bhaiya. Anna of Murugan, no? No, Murugan himself. Murugan Bhaiya is Vinayagar. No, ba? Okay. So he forgot everything. He lost. Did I mesmerize you so much? Oh my God. Okay. Now, the major loss process is OH. So now, how long it will survive? You need to find out how fast these reactions are happening. How do you measure the fastness of the reaction? You need to do the experiment in the lab. NaOH and HCl you titrate. To add, and color phenolphthalein you add, suddenly color, hey, change endpoint on that, finish. But that's not the case. The case is, because you could see the change in the color because the reaction is slow. Suppose fast, you can't see that. How do you see? How do you try to probe the fast reaction? These reactions are second order reactions, they are very, very fast. How do you do it? How do you do it? Use spectroscopic methods. Okay? And now you see. Now, one thing you should understand. When the compound is released, it absorbs light. One. Some compounds absorb light, they emit also light. Because once you are in a high state, energy state, you have to come down. You cannot live in the spinning state. You have to come down slowly, right? Same thing with the molecules. You understand? No words. So, when you are excited so much, you have to come down. The energy has to be dissipated. Then only the ground state survives, right? Okay. The molecule survives in the ground state. So, we can do the measurements based on emission as well as absorption. See? Okay. Now, hey, are you taught in English medium or Tamil medium? MSc? Most of you, right? No problem. But till BSc? That is also a combo. +2? Tamil. I studied in Telugu medium till 10th class. Afterwards, my father put me in English medium, I came back. No, I can't understand anything. He said he gave me slap and go. And I went and that was good actually. parents do good things sometimes, right? Okay, fine. Most of the times, all the times, let me say. Okay, now absorption works on. Hey, what is this? This guy is working. You can see. Okay, this is absorption is something what we use is cavity ring down spectroscopy. Emission less induced fluorescence. I will describe these two. Did you understand why we are trying to do all this? Compounds survive for some time. How do you measure? We have to use the spectroscopic techniques. Karthikeyan is laughing like anything. Why Karthikeyan? What happened to you? Am I looking like a buffoon? Like Vadivel? Huh? What happened? Uncontrolled laugh. He realized, he remembers something. What is that? Hey, did you tell him anything? What's your name? Soundarya. That is the problem, man. What is this? Laughing like anything. Focus. Okay. He became serious now. That is also not correct. Okay, fine. So we are trying to understand the reactions in a way that they react with the chemicals in the regular fashion. They react. But how do we measure the reactions is important. One, use the absorption technique. Two, use the emission technique. Other than titration, actually whatever we do, it is a spectroscopic titration. Right? We do a reaction. How do you measure? You are using some probe. That's a titrometric method. It is a spectroscopic titration. We will see the beauty of it. Okay? Now, this I told you. You have left VOC in the atmosphere. It reacts with OHNO3, O3 or OHNU. This I told you. And produce radical. It reacts with O2 and produce RO2 radical, peroxy radical. And it reacts with NO2, peroxy nitrate. And it loses NO and form peroxy nitrite. And then all these, finally it forms the ozone. And meanwhile in its journey it forms a lot of chemical compounds. So if you ask me, sir, if it forms the ozone, what is the problem? Problem is if it forms the ozone in the stratosphere, it's very good. But it die here itself. It produces the ozone in the troposphere. Very dangerous. You go and walk in the early morning in the seashore, you see the pungent smell. Some ozone formation is there. It's not good for you sometimes. Industrial area beach you should not walk. Okay, fine. Now, this is called, how do we measure do the measurements when the reaction, see what is this absorption, I will tell you. You have reactant A, reactant B, when they are reacting. How do you measure the rate constant? What is the rate of the reaction? What is kinetics? Kinetics is the rate of change of concentration of a species with respect to time. Very good. Oh, sharp guys, man. My God. You are the Einsteins of our country. Okay, good. Okay, this is the rate of change of concentration of the species with respect to the time. Am I right? So, when A is reacting with B, do you need to measure both of them or one is good enough? One is good enough. So, any one of them you can measure. When the rate is very fast, you cannot measure. But certain things, you can use the spectroscopy and measure the concentration, change of concentration of that particular species using absorption. That's the whole idea here. Okay, this is, we have something called cavity ring down spectroscopy. Hey, how many of you have used UV visible spectrometer? UV visible spectrometer. What's your name? Sangeeta. Music. Okay. Did you use? Dhanalakshmi. No? How many, any one of you used? At least have you heard of it? Beer-Lambert's law. Oh, what is that beer? Not that beer. Okay. Okay. Beer-Lambert's law. Right? What is it? All of you are very good. So good. A is equal to epsilon L C. Absorbance is equal to molar absorptivity coefficient or extinction coefficient, path length, concentration. Very good. This is a property of the molecule. Can you change? Actually, this is proportional to LC. correct? Proportionality constant is your epsilon. L is path length and concentration. You have two variables to determine this. Suppose you plot absorbance versus the concentration. Okay, it should be like this. It should be like this, straight. But does it? Does it behave like that? Why? What will happen? Can you, one of you correct it? Huh? Can you tell me, any of you? Don't be afraid. You should come forward. Hey, what's your name? Sharath. Sharath, tell me, how does it behave? You want to say what's your name? Vinayak. Vinayak and Karthikeyan, both brothers are sitting there. Okay, fine. This will go, but it doesn't appear like that. It will become a plateau. Now you are saying yes. All this time you are keeping quiet. Why? When you know something, you should speak out. See the pitch with which I am speaking. Why? Where you go, you should make your mark. You should never forget there is one Rajakumar who taught. That is my intention. When you are sitting somewhere, when you speak, I should not forget what you are speaking. That should be your thought process. Then only you will be recognized. Whether you are recognized or not, you should be able to speak your mind. Don't be submissive. Nobody is superior than you. Everybody born one time only. Right? Yeah, speak out. So, why it will become like this? This will become a plateau. Beyond this, if you measure, this is all bullshit. This is saturation. Detector gets saturated, you can't see the light. Right? Now let us see. This is Beer-Lambert's law. Now we will go into the details. Now, what is this? See, okay, where we started, the U visual spectrometer. The cuvette, what is the path length of the cuvette? Small one, like this, 1 centimeter. Path length is generally the quartz cell, what you get is 1 centimeter. Okay, here, what are the parameters you can vary? Length and concentration. If I increase this length to from 1 centimeters to 100 kilometers, your concentration can be low. You can reduce the concentration because otherwise it will get saturated. Correct? So I can play with the path length. That's what I do here. In 1 meter cavity, we can produce 100 kilometers path length. Is it not amazing? I will show you how it is. There are two mirrors. Sorry, this is 99.995. Okay? And when the light is given, these two mirrors are standing like this, facing each other with no angle between them. Exact line, there is 90 degrees, 90 degrees. Okay? These two mirrors, each mirror will cost you 2 lakh rupees. Highly coated, highly reflective, 99.995 or 9995. What will happen when the light goes in? It gets reflected. Most of the light gets 99.999% light reflected, and 0.001% light goes in. And here this guy is equally bad. This guy reflects 99.99% of the light backwards and releases 0.001% of 0.001% of the total intensity of the light. Because here it is reflected once, here it is reflected twice. So, but it leaks out the photon. It comes out. Then I am here with a camera. What is that camera? The camera name is photomultiplier tube. It counts the number of photons. And it tells you, okay, these many photons came out. It will count. How many photons it will count? 10 to the power of 16 photons it will count. It will count. See the electronics, the level of electronics we have developed. See that? Thanks to engineers. Okay. Now the light, see if every photon comes out, you can record what is that empty cavity. It goes down in an exponential decay. Now I am a chemist, right? I put some chemicals here, and because of the presence of the chemicals, the exponential decay changes because of the absorption. That's all the information we get here. Let us see what we will do here. Now, O'Keefe and Deacon, they tried to measure oxygen, forbidden, doubly weak forbidden transitions of oxygen. Oxygen absorbs in the visible radiation. So, they measured in 1988 from California, Stanford Research Systems, Stanford Research Institute, they have measured it. Those guys done this for one small thing, but it is used in atmospheric chemistry so widely. All field measurements people are doing. Take the spectrometer into forest and measure what is there. Look at that. We have built this in the lab. I will show you a small animation. You look at this. This is a mirror. This is a mirror. I told you, allow the light. See? It is dancing like lol. Lokesh. Beautiful, no? Right? What's Sarath? Vinayagar. Karthikeyan? I don't remember the names. I don't forget the names. I forget your names, faces, but names I will not forget. Okay. Now the thing is, you can see it is a exponential decay. Beautiful, right? Now I am a chemist. I put some masala here. Chicken masala. Achi Colombo masala. Fish masala. Fish Colombo masala, right? We put there. That is chemicals, what you put here. Okay. Now you see that red one. So the tau 0 is the fit of the empty cavity. Tau is the fit of cavity with masala. Right? What's your name? Madhumita. You told me. What's your name? Bhanumati, Indumati, Madhumita. Bah. All typical Tamil names. Very good. Well, of course, we are all Tamilians, you will have Tamil names, right? Okay, good. So, now you look at this. Tau 0 is defined, don't look into the mathematics, this is none of our business. You see absorbance versus concentration, it should be like this, y equals to mx. As long as x can go, y should go. But that is not the case what we are trying to show, see that? That's what I told you here. And the measurements in this region are meaningful, red color. The measurements in this region, you see that it's bullshit. If you say that this is the absorbance, that means you are bogus-ing the community. So you should not report those concentration, the measurements in that region. So now you see, by the time the photon loses its intensity by 1 over E, 1 by E, that is natural lifetime, the photon would have passed the path length close to 100 kilometers. It passes the path length close to 100 kilometers. By the time the photon's intensity goes down by 2.303, what you get is the path length, the optical path length, what you get is 100 kilometers. Damn God thing, because 100 kilometers, what is 1 centimeter, what is 100 kilometers? 1 into 10 to the 7 centimeters, right? 1 into 10 to the power of 7. So you have increased the path length so much, and therefore you end up in reducing the concentration so much. You know why? Otherwise your measurements will be in this region. It's a multiplication of path length and concentration. If path length is so high, concentration has to be so low. Otherwise your measurements will fall in this region. If you increase the concentration so much, you can ask me, sir, you are so jobless. On one side you are trying to increase the path length like mad fellow up to 100 kilometers. But now you are struggling to reduce the concentration to parts per billion. Why, sir? That should be your question. The answer to that is, the concentration of the species in the atmosphere will be in the parts per million and parts per trillion, parts per billion. That means the concentrations of the species molecules are very, very low. So if you want to measure the kinetics of such reactions in the laboratory, you should mimic the atmospheric conditions. When you mimic the atmospheric conditions, what would happen? What is the mimicking of the conditions? Suppose your mother asked Dhanalakshmi to cook chicken, but she will not be confident this girl will spoil the whole thing because people are waiting there to eat. Like me, okay? And Amma will ask, okay, Amma, tell me, how do you cook? Eppadi samakradhu? And she will say, Amma, onion, what is takkali cut pannanu? Takkali, onion, anna? வெங்காயம் கட் பண்ணணும், தக்காளி கட் பண்ண, அது கட் பண்ணி, இது கட் எல்லாம் ஃப்ரை பண்ணணும், போடணும். Then you will say virtual experiment, right? Then if she is convinced, okay, you do it, then she will be standing. But while putting salt, you don't put, I will put, she will say, because no experience, right? Yeah, Amma will put one time, Papa will put another time. Finish. The guest will go to hospital. Okay.
SwayamPrabha. Digital India. Educated India.